So I want to highlight that the purpose of today's workshop is really to bring together the community of scientists that are working on ACCESS. And I'm going to start with this animation, which actually normally runs a lot smoother. It's a bit slow on the machines we have here, but I want to show this as an example of just how complicated the Earth system is, okay? You all know how complicated Earth's climate and weather system is, but what you can see in this image is just one component of what's going on. So this is actually observations of sea ice. It's showing both the Antarctic and the Arctic as you go through the seasonal cycle. And I think something that characterises the science that we do in our community is that many of us are specialists in, for example, one component of the system, specialising in maybe even one particular timescale that we care about. But then when we bring that together in something like an ACCESS coupled model, we bring together science from many different communities. And what that means is that within this room, we have people with different skill sets, in different parts of the Earth system domain. And really the aim in us putting together this workshop is to bring together this expertise and to foster collaborations across the boundaries of these expertise and these skill sets. So that's really the aim of the workshop this week. And to get us started on that, I just want to show a few highlights which kind of span the breadth of the ACCESS science community. And to aid me in this, I'm going to use this ACCESS model framework. Many of you may have seen this diagram before. It's all the components of the ACCESS model that when coupled together make the full Earth system model. And as I said before, in this room there are specialists in, just one component of this area, but all these scientific areas interact in some way and can be thought of as part of the one system. So let's take a tour around this ACCESS diagram. And as I go around this tour, for each slide I'm going to tell you which part of the diagram I'm in by this little graphic in the top right corner. And we're going to start with the land system. And there's a lot of work going on with land modelling at the moment in Australia. Many of you will have heard of the cable land surface model, which is the Australian model that sits within ACCESS. And cable exists in two forms. It exists in a coupled form, but it also exists in an offline form. And one of the things you can do with an offline model, of course it's much cheaper, is you can run different simulations with, for example, new physics or new physiology. So what this slide is showing, this is just an example of the sort of work that's going on, is advanced physiology. So all these green and blue lines up here have different forms of plant physiology encoded into cable. When you include that physiology, what you see is you have much higher primary productivity with a future climate, in a future climate scenario. And that primary productivity results in greater uptake by the land carbon sink. But all this physiology is ignored in the models that we're using to calculate future carbon trajectories. So the implication here is that we may be underestimating the land sink of carbon, and that by putting this new physiology into the global model, we can improve that plant physiology, improve the estimates of carbon uptake. The catch is, of course, that this particular model doesn't include feedbacks, radiative feedbacks, etc., between the biology and the radiation, and that means there might be other feedbacks that come into play when we put it in the full system. I'm going to move to the other corner of my diagram now, right down into the ocean, and in fact I'm going to move to a corner of the globe which is right down next to Antarctica. And what I'm showing here is some output from the ACCESS OM2 ocean sea ice model. And you're seeing here an area right up on the Ross Sea shelf. And these green areas here are actually the thickness of dense shelf water. And dense shelf water is the really dense water that's produced close to Antarctica. It forms on this continental shelf and it spills down over the edge of the continental slope. And as it does so, it actually breaks up. We've discovered in this model that it breaks up into eddies. And when it breaks up into eddies to go down the slope, you say, well, who cares about that really? It's just water at the bottom of the ocean that's going to go down to the bottom. But it turns out that because of these eddies, you actually have a surface expression. So there's this water at the bottom of the ocean is creating a surface expression. And you can see in the colours here from the ocean model that these colours are showing areas where there's high sea surface height variability, which is reflecting this bottom flow. And this is a curious example because it's an example that was discovered in the model, but then when we went to the satellite records, this is actually Matisse's work, but when Matisse went to the satellite records, he could see this sea surface height variability expression in the satellite records. And so it's a case where the models led the observations, and it turns out that we can use this sea surface height variability as a pretty good proxy for the amount of dense water that's exported off Antarctica, which is actually something that's really hard to measure directly. So I like this study because it's actually a case where the models have done things that wouldn't have been possible with observations alone. But of course, models aren't always perfect. So I'll show you a slide where models are imperfect. You've probably all heard about Antarctic sea ice trends in the last few years. This black line here is showing the observed sea ice area anomaly measured from satellite over the last few decades. And you see this kind of gradual increase, and those of you who can remember back to 2015, we were all talking about how strange it was that Antarctic sea ice was increasing, and since then that trend has sort of reversed. And probably the event that has caught everyone's attention is this event here in 2023, which was a huge reduction in sea ice area. Now, just a couple of things about this plot. Firstly, this is anomalies from the seasonal climatology, because of course the seasonal variation in sea ice is enormous. And so this is an anomaly from that sea ice climatology in terms of the relative to the standard deviation. In 2023, the sea ice sort of looked like this. So this is the anomaly from the climatology in June to August in 2023. And you can see pretty much right around Antarctica, there's a big reduction in the sea ice. So how does our model do at this? Well, interestingly, the ACCESS-NRI model does a really good job of sea ice right up till about 2015. This is the colours that you're seeing here, but it completely misses this 2023 event. And it doesn't matter which sort of forcing you use. These are two different atmospheric forcings, a JRA GOGO and a NERA 5. Both of them miss this anomaly. So this is an area where the model is not able to recreate what we've observed, and we're still puzzling out why that is and what might be missing. Let's move up to the atmosphere, and this slide's from the CLEX OS2200 team, and OS2200, for those of you who haven't heard of it, is an implementation of the UM's regional nesting suite that allows us to run at 2.2 kilometre resolution over the whole of Australia. Of course, it's a pretty big simulation, so it's generally done in short bursts. I think the nice thing about this model is it's not something we're using for forecasting, it's something that can be used to understand mesoscale processes. And that's what this example is showing. So these are some radar images from Townsville. These are synthetic radar images from what you get out of OS20, or rainfall for what you get out of OS2200. And you can see that for different prevailing weather patterns, whether the wind's coming from blowing onto the land, along the shore or blowing offshore, you get very different precipitation conditions. And by digging into this model, we can get much higher resolution and understand, hopefully, how large-scale patterns can modulate the coastal rainfall. And so this is an area that we're taking a lot of interest in to try and better understand how these mesoscale processes, and to build the tools that allow us to understand those mesoscale processes. Going even further into the atmosphere now, and we're now into the realm of aerosols and atmospheric chemistry. This is a slide highlighting the role of aerosols in the Southern Ocean, and most of you probably know that there is a significant bias in shortwave and in temperature in the Southern Ocean, in pretty much all climate models actually, and there's a lot of interest in knowing how to fix this. And it turns out that aerosols are also poorly represented in our models in this region, and you can see that by the black is showing the observations here at Macquarie Island, and all these other lines are down the bottom are showing some output from the ACCESS model. And so, of course, it's possible that there's a link between this radiative forcing bias and the Earth's radiative balance. So, so there is a fix here. This light blue line is a way of fixing the aerosols, but if you look at the actual effect on the outgoing radiative bias, the fix makes the radiative bias worse in the Southern Ocean. So if you need more details of this, you can talk to Sonia. But I think I think it's again an indication that we've probably got some way to go in perfecting the models that we use. And off to the very lower right-hand side now, I'd like to highlight some work that's going on in the ocean biogeochemistry space. So it turns out that in a system model, having just the biogeochemistry of the land surface is not enough. Roughly half the oxygen in our atmosphere comes from the ocean. And so we need a good way of estimating ocean biogeochemistry if we're going to get that bit right. So the Australian biogeochemistry model is called WOMBAT, and WOMBAT's undergoing some significant renovations thanks to Pierce Buchanan's work. And we have a different way of incorporating WOMBAT into the ACCESS framework, which we're building at the moment, and is pretty much built. So in the future, there's going to be, well, there is already 2 versions of WOMBAT. This is WOMBAT Lite on the left, which has, as far as biogeochemical model goes, it's fairly simple. WOMBAT Lite is a significant advance on the WOMBAT that we've been using up until now, particularly in areas of iron and carbon flux in the Southern Ocean. But looking forward, we'd like to also have the capability to include more traces, and this is what's going to happen in WOMBAT Mid. This makes it more expensive, but it also includes more processes. So perhaps one day there'll also be a full-strength WOMBAT. I think that's in Pierce's plans, but at the moment we're looking at implementing both WOMBAT Lite and WOMBAT Mid into the ACCESS framework. Initially in ACCESS OM2 and then in ACCESS ESM in time for CMIP. Okay, so something I didn't tell you about when I first showed you this diagram is that the ACCESS model framework diagram is that there was a part missing from it, and that part is the cryosphere, and in particular our ability to model ice sheets. And this is something that that ACCESS-NRI was not funded to do originally, but we've got extra funding to be able to incorporate ice sheets into the ACCESS suite, and we're going to begin that work soon. We've gone through the process of selecting the ice sheet model. Felicity's going to talk more about this in her keynote today, and I guess I just wanted to highlight there is already some capability in running ice sheet models. They're not coupled to the ACCESS framework yet. We hope in a few years that they will be. And what this slide is showing is it's showing simulated grounding lines from different points in history with and without climate change. And so the intent here is to be able to use this model to do detection and attribution of how much climate change is contributing to the change in retreat of these key glaciers that are in Antarctica, which gives us more confidence for how they're going to work in the future. And finally, I've got an example here of where we put it all together. This is some recent output from ACCESS ESM 1.5. So ACCESS ESM 1.5 includes pretty much all of this diagram. Strictly speaking, doesn't necessarily include this corner, but it does include a full representation of the carbon cycle. And it's also, you know, it's got the advantage of being the fastest full climate model that we can run, and perhaps the easiest one to get going. So ACCESS ESM 1.5 is seeing a lot of use. And this is some results from Gabriel Pontes at UNSW, who has been looking at the meridional overturning circulation in the Atlantic Ocean. And something you'll see in this lower right diagram is that most of our CMIP models show a weak negative trend in the AMOC, but the observations tell us that actually the AMOC is reducing at a greater rate than these weak negative trends. So the intent of this work is to see whether these trends, this mismatch between observed and trends in the historical record is due to the role of freshwater forcing from Greenland melting. And when Gabriel adds freshwater to his simulation, you see that there is a shift in the trend, and it's much closer to what we've observed in the historical records. So in other words, there is a chance that the reason our models don't match AMOC trends is because of the lack of freshwater forcing. If we put that freshwater forcing, add that freshwater forcing going forwards, then you can see there's a substantial reduction in AMOC strength going forward into the future, which is a scenario that is, I guess it's been hypothesised for a while, but it's good to have these realistic simulations to show this. So that's the end of my tour through the ACCESS science framework. There's a few other things that I just want to highlight before we start the program proper, and that is that one of the reasons we're here and one of the reasons ACCESS-NRI is funded is because doing science with the ACCESS model can be very complicated, and in the past we've found that doing that science is always complicated by the technology, and so there's a certain level that you have to get up to be able to interact with the ACCESS model, and part of our work is to try at ACCESS-NRI, part of our work is to try and lower that barrier and try to make things not just easier to use, but actually easier to use properly. So easier to use with reproducibility, with provenance, and things like that. So I just want to show a few examples of where we think we can make a difference in that space, and perhaps where we have made a difference, and use that to shine a light on where we see us going in the near future. I'm starting in the land again. This is not my bias. You know, I'm not a land scientist, but why always start with the land? Anyway, here we go. So we're starting with cable, and one of the things about cable is, in my view, it's been software that's been managed by scientists for a very long time, and I'm a scientist and I'm not a very good software manager. It turns out most scientists are not very good software managers, and this is, I think this has actually really put a handbrake on cable development for a long time, in my opinion. Cable's now in GitHub, and the community has come on board to that. And what I'm showing here is an example. I know you can't read this, you're not meant to, but this is just an example of a GitHub issue where issues were identified by the community. They were flagged. In the code base in GitHub. The solution came from the community. It was developed, documented, put into GitHub. But then when that fix was made, it wasn't just put there and left. It went through BenchCab and me.org, so ways to evaluate and test what was going on. and it went through community review, and finally it was complete. So this is an example. I mean, it sounds like a small thing, but it's something that couldn't have been done before transforming cable into GitHub. I don't think it can be done under the old way that we used to run it. And this is the way going forward that we would like Access code and the Access framework to operate. So that's just one example of how an open and community-based process can actually help the development of the model. And I want to stress here that ACCESS-NRI has lots of expertise, but it doesn't have a lot of scientific expertise, and the scientific expertise needs to come from the community, and we can provide the software expertise to help you out. And if we can work together on that, then I think we can do much better than we've done in the past. We've also put a lot of effort into evaluation and model diagnostics, and some of you will know from yesterday's training day where we had a CMIP7 evaluation hackathon that we've been working hard on ESM Val tool. There's publicly released workflows of how to use ESM Val tool. We're developing recipes to allow us to evaluate models. We're running these hackathons, and because ESM Val tool is an international program, we've also been interacting with the International ESM Val tool Consortium, and we're a part of that consortium and actively contributing. So this is a tool that we hope will have more uptake in the coming years. One of the main advantages of it is we hope we're going to have the evaluation system in place before the model is running, and that's something that's never happened in Australia before, to be able to evaluate the model before the model is there. But that's where we'd like to be, because in developing the model, we want to be able to make use of these sorts of tools to better understand how we can optimize and calibrate and understand our models. And something else I'd like to highlight is that last week, or maybe it was the week before, we made a full release of Access ESM 1.5. What's the big deal, you say? Access ESM has been used for 5 years or more. But actually, it's been quite difficult to run and quite difficult to find out how to run many of the Access models. So by making this release, we've released 2 initial configurations. There's going to be more to come. There's a way to build these models that we are recommending, which enables us to know how the model was built, how to recreate that. And in fact, the output from this model is bitwise reproducible with the version that we picked up from Cyro. And so being able to do that is not actually easy, to be able to run things in a way which are bitwise reproducible. But it's a huge advantage for being able to test the model and to know whether changes you've made have altered or have degraded the model. A lot of the configuration details are done through GitHub, so you're able to run these models through GitHub or by picking up GitHub branches, and that enables you to track what you've done. We also have automatic post-processing, and we've done a lot of updates to the tools that allow you to do reproducible results or to sync your output. So if you're an Access ESM 1.5 user and you're about to start a new experiment, we'd really love you to give this release system a try. This is the sort of system we're going to be releasing many other models on. We've already got it for Access OM2. We will have it for other models soon. And so it's something that we really want community engagement in, feedback. If things aren't working for you, please tell us straight away. We're there to help. So the other things that are on our list for the coming year at ACCESS-NRI is there's a lot of effort at the moment going into the CMIP7 process and the development of Access ESM3. We've got some working versions of Access OM3, of AM3. There's a lot of work going on to the next version of cable. There's going to be some proto version of Access CM3, which is running. So the kind of Access 3 generation is under development, and it's something that we're going to be working on a lot during the next year. We're going to do formal releases, hopefully, of ESM 1.6 in time for CMIP7 Fast Track, of Access CM2 as well. You'll hear more about ISSM today, but we're aiming to adopt ISSM for ice sheets. We're thinking hard about future technology and the role of AI/ML and GPU readiness, and so we're going to put together a strategy for that, and there'll be more on this topic later in the week. And we're getting to the process of releasing model output data and other data releases, as well as being able to catalogue and find this data on the NCI system. So I'm going to stop there. While I'm stopped, and if there are any questions, I'll just leave this animation up. This is something else on the horizon. This is a 1/80th degree simulation of the Tasman Sea that is actually done by Ashley Barnes. I forgot to put his name on there. What's actually plotted is wind stress curl, and wind stress curl is a really cool thing to plot because you see the fast, large-scale atmospheric motions which drive large-scale Ekman pumping in the ocean. But what you'll actually see is once you model the ocean at high resolution, you develop all these small scales of motion, and those small scales of motion also alter the wind stress and thereby the wind stress curl. And so you can see this slow, fine-scale ocean dynamics overprinted with the large-scale atmospheric fronts. And so I thought I'd leave that for you to keep you entertained if you have any questions. Thank you.
Thanks, Andy. Great overview of what's been happening. I guess I'm wondering in terms of the NRI's future strategies, what do you see as the biggest things that might shake things up in terms of software? Is it AI and ML, or is it trying to optimize the codes for higher resolution? What do you think is going to be the biggest difficulty coming forward?
Yeah, so I guess the reason we picked these two out on this slide is because they are significant changes, potential changes to how we work. And I think some people see AI/ML as a disruptor, and maybe they're seeing that because they're thinking in terms of forecasting. I mean, potentially they are a disruptor. For example, our atmosphere model in the climate system comes out of the forecasting world. If we can do better forecasts with AI and ML, people are going to put less effort into the forecasting models. So we might see a slowing in the pace of development of those models. And I think that is a risk, but I think there's also a lot of benefits from AI and ML. So I see it as a change, but I don't see it as a threat. I see it much more as an opportunity. You know, ways to use AI and ML to get extra information out of models, or to tune AI/ML models to get information out of observations, or to parameterize fine scales much better than we've done before. I mean, you know, at least in my science community, a lot of people put faith in these parameterizations that were written down in the 1970s, purely empirical. Surely AI and ML can do a better job of those parameterizations than some guy sitting at his desk in the 1970s. So I actually think there's a huge amount of opportunities for AI and ML. I see GPU as a threat, and the reason I see GPU as a threat is because the current generation of models we're running can't run efficiently on GPUs, but the computer centers are looking at it and saying, oh, you get more flops per dollar, therefore I'm going to convert all our cores to GPUs, and then we won't be able to run large-scale climate models anymore. So I think that's a real threat and something we're trying to adjust to. And I think within Australia, you know, we're well positioned because NCI has been very supportive of the climate community. So we would still expect there to be CPUs on NCI going forward. But that mix of hardware, it just evolves so quickly compared with the software. And yeah, so I see that as a threat and a bit of a disruption potentially. So.
Thanks, Andy. So one idea that's floated around a little bit in the ESM community is having a faster running, lower resolution version of the Access ESM. I was wondering if is there still some interest in maybe trying to halve the resolution. I was thinking both on the atmosphere and the ocean side could potentially get a 10 times speed up that way.
Yeah, you could. So I actually think that in terms of a speed up, where we're really limited at the moment is in the atmosphere. So the ocean can scale better than the atmosphere because the algorithms are so different. So I would very much like to see a low resolution, the capability to run a low resolution atmosphere. And I occasionally hear rumours that there is an N48 version of the UM that is used in UK ESM, and there might be the opportunity to port that. So I guess I see that in the long term, it would be good to have a whole suite of configurations that span, you know, from idealised to low resolution to higher resolution to, you know, high-res MIP type resolutions to the insane sort of resolutions that Christian Jakob's talking about for 21st century weather. So we're going to have this whole spectrum. So there's a lot of places we can have input there, right? So I think that's definitely possible. But if we invest in a low resolution, that'll take time away from, for example, investing in a fast spin-up for ocean biogeochemistry for the standard resolution, or investing in the highest resolution. And so there's always a balance, and it's a zero-sum game in a sense. My hope is that we can work with the community to try and better understand what the most effective way is to deploy our efforts. And that actually really needs us to understand who's using models, who's going to run models, who can help with the science development, and so on and so forth. And that's something that can come through the working groups. And maybe my vision for once we finish or make progress on the development of these ACCESS-3 models is to have a process within ACCESS-NRI where through the working groups people can propose new configurations that would be used by a community. And that's not to say one person can say, I want to use this model with this particular stuff, therefore I'd like it developed. It needs to have a little bit of community support so that we can put the effort into software engineering it. And so then we could have a situation where people would propose configurations, we would figure out how to do it, and decide where to prioritise it amongst our advisory committee. I think we have to get to a certain level before that. We have to release legacy versions. We have to be able to release, you know, the next versions of Access. But once we've done that, then adding more configurations to the mix should be easier than it currently is. I think that's half yes, by the way, just to summarise.